Good morning and welcome to the conference. I guess I'm honored to be the first one to present a talk besides the introduction. Obviously, this is a preview of my August presentation because I apparently thought it was going to be in August, not July.
2015.
Oh.
Is this a repeat?
Wait a minute, let me make sure I got the right one here. Just a moment.
Bottom one.
I got the right one.
Okay, that's okay. You probably just didn't change it.
I started with my last year's presentation and ended up with wrong date. Anyway, just a little bit of background of me. Been working on gravity for 10 years. In response to David asking me to help with a gravity experiment. And during that time, I realized if I was ever going to get anything done in gravity, maybe I shouldn't be paying attention to trying to prove somebody wrong. And so I kept telling David, halfway through the film, he said, "Dad, you never say Einstein's wrong." And I said, "Dave, I haven't taken the time to prove it." And so he was very frustrated with me, and I didn't, even until last year, when I found an article by Robert Johnston, and let me give you a little background anyway. This is before Robert. My concern about special relativity was generated because observer B on the Earth sees something different than observer A, and hence you need to transform what observer B is seeing relative to A, and you end up with special relativity equations. Assumptions are made, models are built, equations are developed, and the result is we have paradoxes. So what got me started was I was on the internet looking for stuff, and I got onto Robert Johnston's explanation and derivation of the equations. That's the link if you want to go look at it. It's that link is referenced in my paper. I have nothing against Robert Johnston, but when I saw his model, they looked wrong. The model itself, the pictures, look wrong to me. This is his text. This is the very text he has in that paper, and this sets the stage, and you've all heard it, but I'm going to take time to repeat it. Imagine a spacecraft passing the Earth with velocity v. On the spacecraft is an observer and an apparatus that will flash a beam of light across the spacecraft perpendicular. He flashes it straight up.
Whoops.
Wrong button. I'll get there. Boy, it doesn't take long to get past, does it? But on the Earth, there's another observer. According to the observer on the spacecraft, the light beam travels at a distance w, which is the distance from the floor to the ceiling, where w is the width of the spacecraft. He calls it width, but to me it's height. But anyway, however, the observer on Earth will see the light beam cover a greater distance due to the motion of the spacecraft. The cause of the difference is in the motion of the spacecraft. That's the answer, whether you agree or not. Due to the motion of the spacecraft, while the light beam is en route to the ceiling, so it kind of gets lost in this screen, Dave. I'm not sure what particularly happens. So let's take a look at the pictures and just make some comments about it. The one on the left is the observer A. He's on the spacecraft. The spacecraft itself is, in fact, this white object. He's timing something, apparently. There is a beam of light going straight up, as Johnston says, and it has a height of w. What's not there, there's two things not there. What's not there is the velocity. So apparently observer A doesn't know he's moving, and that's kind of an accepted idea, that you can be on the space shuttle and not really know it's moving. But the other thing, and I guess he doesn't know it's moving because he can't see out. We can see in, but he can't see out. He can't see the Earth. He's encapsulated. He's limited in what he can see. And the other thing is, there's no source for the light. And I'll make that point there, and I'll make it again later. There's no source for the light, but you're going to assume that that the thing is pointing this way, straight up, and the light is going straight up. That's what he's telling you. So that's what you believe. But when you come over to this one, by the way, this is 2 spaceships. This is the starting point of the spaceship, and then this is the finishing point of the spaceship. And again, the source is not there. If I didn't know by reading what he says, I could just as well easily assume that that source was at an angle, shooting the light to the right. I mean, I don't know why they don't show the source. I mean, you have to guess. You have to make the assumption of what he says, that maybe that's the way it is, but it's not there. The other thing that's interesting is observer A is gone. Why is he gone? I call Robert Johnson. I said, how come there's no observer A in the second picture? He said, well, I think he had to go to the restroom at that point, and so he's not there. It seems odd. What I get out of all of that is we're getting a limited input on what's there. As a scientist, as an engineer, I want to know, where is that source and what direction is it pointing? Okay, so that bothered me. No, this first one didn't bother me at all when I first looked at it. But this one, this bothered me. Having studied light, and I think the reason why this meant something to me is that I had recently been studying light. And by the way, this is kind of has a subtopic here in terms of light. Is that I'm pretty much aware that if this spaceship the light is here and it's gonna move up. So why is it going forward? That's explain the motion. Just saying it's motion didn't get it for me. So I looked into it a little bit further. This is a repeat of what I just said. That's the white spaceship. Doesn't know he's moving, and the laser source is not showing. And this is the same comment about that. Observer A is gone, and there's no laser pointer. So I'm gonna. I don't know about the picture, Dave.
That's okay.
Can I move to the middle?
Yes, you can, absolutely.
Okay.
You want the lights off?
Please.
Okay.
Okay, so I'm going to go through some demonstrations. I'm going to do what the guy on the spaceship, the observer A, has done. Okay, he shoots that. Now I'm pointing it straight up. He shoots it to the. If I push the right button, now my slides. Okay, everybody see the beam?
No, don't see the beam.
Don't see the beam.
Don't see the point there.
Of course you don't see the beam. You can't see light. You can't see light until it hits your eye. That's when you see light. Okay. So my wife, well,
I can do what you want me to do.
spray. My wife says, well, I know the answer. I was telling her what I was going to do, and she says, I know how you can see it. I saw on TV. All you do is shine hairspray. Does it work? No?
There, you can see it. I see it. There it is. See it? Dad, don't move it. See it? Here, you can see it. See it?
It's in the spray. Right in front of you.
Oh, okay. So now you see the light beam, right?
Yeah.
You sure? No, my answer is no, you don't see the light beam. What do you see?
Scattering off of the particles.
You see the red light scattering off the hairspray. So what you're seeing is red hairspray particles. You're not seeing a beam. So you could go back. Boy, did I go back. You already see my answer. Forget it. I can sit down. So what you're seeing is a high-intensity red light scattering off the hairspray particles, and it scatters. Who didn't see the light beam? Everybody? How is it that everybody sees the light beam? Okay, you know, if I put that, I don't have the hairspray now, but at least we can see the dot on the ceiling. Bruce over there, I think he sees it. Ray, you see it, and you guys in the back, everybody sees it. Why is it that you see it? What's happening? The light, there's so much red light hitting the ceiling, it scatters. We always think of reflection, but it isn't reflection that's happening, it's scattering. It scatters, and that light hits the ceiling, and part of that light goes right over to Bruce, and part of that light goes over to Ray, and part of it goes to Ron. And if you stop to think about it, you could have walked all over the room and you'd still see that light, and there's an image of that light everywhere in the room.
What's the difference between reflection and scattering? Aren't
Well,
you seeing reflections?
Since I learned about scattering, reflection, I more use it with a mirror. When you shine this light off a mirror, it reflects, and there's an angle of incidence, an angle of reflection, and it doesn't scatter. It may scatter a little, but we as our eyes don't see it. But when it hits the wall, it's scattering all over the place. That's the only way you can see it. Otherwise, you couldn't see it. That image has to be there.
Yeah, and I respond to that too. Another way people talk about reflection is it's coherent scattering. In other words, there's
Yeah,
particles
you
in
can
the
say
mirror, each one scatters, but because their waveforms join together, they scatter in the same direction. So it also is a scattering process.
Okay, that's one point. I'm going to make a second point, and this has to do with my face. Okay? And it has to do now with ambient light. This was a coherent red light going in a straight line. Light off of these fixtures is white light, and it isn't going in a straight line. The light is coming at me from there, from those, from there. It's white light is hitting my face. Oddly enough, only the color of my face scatters. Color off of here, color off of my hair, color off my glasses, that scatters, and it sends an image to Bruce, it sends an image to Ray, and it sends an image to Ron. To your dismay, there's an ugly face all over this room because it's a scattered image off of this object. Doesn't matter. When you really stop to think about it, your face is scattered around, and so on. There is another point. Bruce only sees my right ear. Ray only sees my left ear. People in the center see both ears. You're not seeing the same thing. It's a slightly different image as you go around the room looking at me. So your conclusion is, yeah, that's Bob D. Hilster standing there, but every one of you has a different image, scattered from the white light off my face around the room. So, where does that put us next? So we did the red laser beam, and maybe it would have been better if we had a pretty model to see her face. Okay, this is just a summary, but my point basically is there are images scattered from one event. I'm going to start talking about an event. At one instant of time, ambient light hits my face, that one event projects, then another, and what you see.
Microphone up, please.
Composite of that, of those individual events. Okay, so now I'm going to go look at observer A on the spaceship and try to decide what I think he sees. Okay, I'm going to assume that the velocity of light velocity is c. that it moves from the bottom to the top at the speed c and is independent of the source velocity. That's sounds like relativity, right? You think I'm back where I'm started. I'm going to assume that the spacecraft is moving at half c and in the x direction to the right. And I'm going to assume that light moves in a straight line. So is that what you get when that happens? But the spacecraft is moving. Here you see it's, he says no, it's not. He doesn't know it's moving. And so he might not use this conclusion. Now I'm adding to what the author added to because I'm moving. I got the spacecraft moving at sea. So, by the way, I obviously added the source. Put the source there. If you don't understand that I think that's observer A. David doesn't like my drawings very much, but it kind of gets the point. And the spacecraft's moving to the right, and you please imagine there is hairspray particles in the room. Because you're going to see what looks like a beam, which is really scattered light, red light off a hairspray. So what you expect to happen is that the ship's going to go to the right, and I'm going to do it in bursts of light, bursts of red light. So what you would at first think you're going to see is that light's going to go straight up from the source, but unfortunately the ship moves at the same time, and what really happens is that when the ship moves at the same time, the light is continuously emitted, that burst is continuously emitted. It started at this point, it was emitted to here, and set up that stream of hairspray particles, and now the pointer's over here ready to do another one. Whoops, wrong button. And as you imagine, or could imagine, that's what I would predict would happen from my assumptions. Not that it goes up. The light goes straight up, the ship goes to the right, the observer A moves with the ship, he's moving, he was over here and he's moving away from that. And so what you end up having here is you got light moving at sea. So there's going to be some, if I can call them photons for a moment, photons here, photons there, just hitting the hairspray particles. And guess what they're going to do? They're going to scatter. They're going to scatter from that point, and they're going to scatter from here and from here and from here and from here and here. And one of the directions it's going to scatter is right to him. Right to that subscriber. That's an old telephony problem I have. I'm practicing this speech. In telephony, I worked for about 5 years on line circuits, the circuit that connects to your phone back, okay? And so we're always talking about subscriber A, subscriber B. So every once in a while, my brain goes and picks up that word and says, you're not talking about observers. Don't you really mean subscriber? So this is observer A. So what about observer B? Remember, at that instant of time, when it scatters and it moves at speed c here, it's going to scatter and move in all other directions. I'm talking about the one event. And I contend that observer B on the Earth is going to see the same image as observer A because he's observing the same event. And this light scatters off of here at speed c. And I don't understand how he would see anything different unless something can change after it scatters and make this different. You can actually make other arguments for how or what observer A might see. I would contend that it doesn't matter what observer A sees. When that light scatters off of those particles, that image is going to go this way and this way. So if he happened to see it vertically, they both see it vertically. If he happened to see it moving to the right, moving to the right. Now, what I'm trying to do is explain my opinion of how light works in this situation. Apparently, other people must have a different idea of how light works, because as the ship moves away, somehow that light goes forward. Not for A, but for B. And they make this statement all the time. Because of the motion of the spaceship, this is what you're going to see. If you have a theory of how light works, apply that. I think that's one of my next slides. This is my opinion, a final opinion. Anyway, I want to go on to this. If you don't agree, take the event, apply your theory of how light works, decide for yourself what A sees and B sees. And then you can decide whether it's needed or not. Right now, I'm convinced you don't need it. If you see the same thing, you don't need equations to transform something that's the same. Length does not contract. Time does not slow down. Paradoxes do not exist. And special relativity is not needed. So I'm going to go back to gravity. This is going to be my first and last talk on special relativity. And I thank you for your attention.
Any questions or comments? Go ahead.
Does this kind of support the concept of an absolute space, because the light is actually released at a specific point?
Dad, can you stay up
and
there?
it does not,
Dad? Dad? You're still up here.
I'm sorry, I'm directing. Stage front, please.
I tried.
There you go.
Does this support the concept of an absolute space, because the point at which the light is released is, the light does not vary from that point except in the direction in which it was released, and the observer would see the slanted beam, with the hairspray?
The reference point, that's a good question, by the way. At first I thought, I'm not sure I got the answer, or an answer. I don't want to say I got the answer. Okay, Robert, get your head back on.
Absolute space.
Yeah, it's the reference. Okay, it's the reference. Okay, now if I go back to well, yeah, I kind of have to think. If you go to this figure, what you're seeing is there's an angle here. There's an angle from. You might have expected to go straight up, but there's an angle, and by the way, if it's moving at half c, that angle is 30 degrees. Okay. Ironically, this guy can look at that angle and tell how fast he's going. Now, in terms of absolute space, I don't know, but in terms of the speed of this light, you do know. In other words, if you knew what that speed of the light was in the spaceship, then you know what the speed of the ship is because of the angle. Now, how does that play out with the universe? You got to tell me what reference you're talking about. I don't know where the absolute comes from in that case, but you do know this. The other thing is, if the ship is going this way, and on the roof you see that the light has moved over this direction, then you know you're traveling that way. You not only know your velocity, you know what direction you're traveling. The problem is trying to measure that. I did some calculations, I didn't put it in the paper, but if you take the space shuttle or the space station 17,000 miles an hour, that angle, if I'm right, or if this model, it's not whether I'm right, but if that model, that idea is right, that's such a very, very small angle, because it's a difference between the speed of that red light and the speed of the ship. It's a small angle.
I guess 10 years ago, my brother and I tried to run an experiment like that. You can get very sensitive diodes, and we didn't measure anything other than the noise. But after analyzing it, spending a lot of time, we finally figured out the real clue is how do you generate the light. there's no way of generating a beam that isn't affected by the motion itself. For example, if I put a light down here and a little hole above it, as I'm moving, there's
Yes.
movement between the hole and the
If-
light, and it actually causes the aberration to come out that other direction.
Yeah, well, no, what happens, because I looked at that as well, I didn't put it in the slides or the paper, but what happens is, I'm gonna do a motion, I won't be able to talk. This is the light, and this is the light beam that's going to push it in a horizontal direction. And so it's gonna go like this. And the observer A is gonna, in that case, is actually gonna see a straight up line.
Think of it as a bullet. Shoot a bullet out of a rifle. If you're moving on the rifle, there's an aberration because
happen.
of that tube. if
But,
will.
you know, in absolute terms, I don't know the answer. I don't know whether that component of horizontal velocity is there or not. I made the assumption in the diagram, it's not there. I think the conclusion is valid under that assumption. But if someone could show that, in other words, if you could actually go a half the speed of light and you found out that this was straight up and down, that would prove the point that there's a horizontal component.
We tried to use the Earth's spin to measure it.
That fast.
And in fact, there's a guy that claimed that he did measure something on a boat, floating a boat and turning the boat around. But my looking at it says that's impossible, that he couldn't measure it.
But what you're saying,
Yeah.
if I understand, it really comes down to the mechanics of how the light's released.
Exactly.
And I agree, I mean, looking at our model, that's really important.
Yeah.
How is light being released
Exactly.
actually from that?
Yeah.
And what you're
Okay.
saying is the barrel, but people
Exactly.
don't understand what it is. It's the actual movement of the barrel, it's coming out, there's forces on that.
Yeah, yeah.
And that's really, really.
I likened it to shooting a rifle from a moving truck, for example.
Yeah.
Right.
What
But
happens?
people are thinking that.
You can
because of
shoot
their
somebody
movement,
else
yeah,
that's straight across from you.
But it's actually the release.
Bill?
I'm going to tell you all something I don't think you know. The first inventor of relativity theory was not Einstein. It was Henri Poincaré. He published it 1 year before Einstein, and he published the refutation of relativity theory, and that caused Einstein to never receive any award for relativity theory. His only Nobel Prize was for his wife's work, not his work, on the photoelectric effect. And by the way,
What good are wives anyway, right?
Yeah, you know, but the data miller actually could be maybe more responsible for that situation that actually did not get it right, because that guy actually measured the ether drag, essentially by doing the experiments of maximum orbit time on the
Yeah.
higher elevations. So here one should consider, I mean, the situation with the ether. So the light is propagating in the ether, and now it depends if that is kind of absolute frame in that particular spaceship. It's part of that, background, the substrate. And then, you know, take into account how actually photons, those structures propagate, then you can figure out.
I have another misconception I want to cover. The photoelectric effect gave the idea that light is a photon,
Yeah.
as a particle.
Yeah.
That was refuted when the photoelectric effect was done not on a crystalline metal, but on an amorphous metal, the same metal. You don't get the photoelectric effect. It shows that light is only a wave, it's not a particle, and there's no such thing as a photon. And that information has been dispersed worldwide, but for the politics and the scientific community, they ignore it. But if you're an engineer and you build the optical chips for a computer, you have to put the antenna in, which is like the lattice, in every optical chip, or it does not work.
Okay.
And that's known by people who are electrical engineers. But our physicists say, oh, no, their work doesn't count. Only counts what we do in physics.
Okay, I'd like to get back to the original point, though, that the light could not just move forward. Could also, it could move horizontally as well. Even if you don't know that answer, my point is, whichever way it is, B will still see the same as A. Doesn't matter which way it is. That's one of the main points. It could go forward, it could go straight up, it could go backward. But if A sees it that way, because of scattering of that image in all directions, B sees the same thing as A, and relativity, I'll go back to the point, is not needed.
Okay.
My comment would be one more actually, that we even should not be concerned what we are seeing or what somebody is seeing, but actually what is the reality itself, objective reality, and then look at studying that reality in different ways, and then find some common ground, something like that. But I found this contribution very, very useful.
All right, thank you very much.
Okay, we're gonna have to stop. Okay, thank you very much.